This is Hess's Law, Lecture 2. And last time, I took you through and showed you the interconnectivity of the individual heats of formations of elements into compounds and showed you how we can use those individual heats of formation to get the overall. Nice visual way to look at. Right here, I have my elemental states, and my elemental states are the state at which elements exist without measuring how much energy it took to form them. They were essentially formed during the Big Bang or some time afterward before we start measuring. We make these the zero delta H's. They have zero heats of formation. This is our baseline. Okay? These things exist without us giving them energy. Now, from this baseline of zero heat of formation, we know that when they bond, for the most part, there are some examples where they become even more unstable, and that'd be a positive heat of formation. When, let's say, carbon, hydrogen, oxygen form to make propane, we notice that there's this amount of energy released. So what happens is the propane becomes a little more stable than the individual elements, which is one of the driving forces. This oxygen here is a zero, so it's not part of, it's not added to this delta H of formation because it's already an elemental state, so there's no change. So this entire change of heat of formation, when we form these two reactants from their elements, is just due to the propane because this is still a zero. So we form propane and it takes this amount of energy. So what I want you to understand is that this is the reactants. This line represents the potential energy, so to speak, of the reactants. Even though I have enthalpy here, we can also put a line here for potential energy. And because it lost only a little bit of energy, it still has a lot of potential energy. And we would say the reactants have a lot more potential energy than the products. Now let me just write this a little better. Okay, so let's make this potential energy go to like right here, and we'll make this the zero. All right, for potential energy anyway. The products, their potential energy is lower because what? Well, they did collectively lost a lot more energy when they were formed. So when CO2 and water were collectively formed from their elements, there was a lot more energy released. That makes a lot of sense. CO2 and water are much more stable than the propane. And that's why things that can explode or react or burn have a lot more potential energy than things that do not. So you can see that this green arrow shows us the major change from our reactants to our products. Okay, and this is the delta H of the reaction. Okay, and very clearly it went down a lot. Okay, and we can actually calculate this. But since we want to show that energy was lost by the system, by the reactants, we want to show a delta H to be negative. The only way to calculate that negative and come up with a negative, we're going to have to use the products or the summation of this larger negative number minus the smaller negative number. So what we're going to get a negative is a delta H of the reaction has to be the sum of all the products' heats of formation minus the sum of all the reactants' heats of formation. Okay? And that's how we figure it out. That's why we do products minus reactants in this case, because that will give us a number that represents directionality in the area that we want. So exothermic reactions release heat because the energy is being lost by the system. So the delta H, which by the way equals Q of P if it's at constant pressure, and the Q is lost. So therefore it must be negative. And that's what we did here. And we did some problems. Case in point, here's one of our problems. And again, this is how we would do it pencil and paper. Here's the propane, here's our oxygen, here's our products. It's balanced. Delta H has to be per mole. So when we go to the tablature, okay, we'll see that propane does not have a heat of formation of negative 394. It has a what? heat of formation of negative 104. Where am I getting that from? Tables. And why am I putting it over here? Because it's products minus reactants. So this is a reactant, so its values will be on this side. Okay, it's very important that you don't make the mistake. You should understand why it's products minus reactants. Oops. Because there's going to be a scenario I show you today where it's not. We want to show negative energy. So you want to think about, if you want to look at terms of potential energy, if you make this 20, let's say kilojoules, or we'll just make it joules, and if you look at this as 100, we'll take the potential energy of the products, 20 minus the potential energy of the reactants, 100, and what do we get? Negative 80. So that's the reason why it's products minus reactants. Very important you understand that. So when we do the work, we look up the propane. We see it's negative 104. There's only 1 mole of it, so I don't times it by anything. This is already an elemental state. That's why it's 0. Okay? Now the other elements are the products. That's your CO2. And there's 3 moles of them. Heats of formation are per 1 mole. And there's 4 of the waters. We look them up in the tablature, multiply them together, and notice they're minusing the what? Products minus the reactants. The summation means we're adding the individual per mole values. And we get a negative 222, or approximate. And that represents this change right here, negative 222, probably kilojoules. Yeah. That's what this represents, this green arrow. So hope that's clearer. Now, why did I go over that again? Well, because there's another scenario which you have to understand. So how does the idea of bond energy or data from bond energies help us in determining delta H in the same fashion or very similar fashion as heats of formation? Well, first of all, let's look at this graph. This is interaction energy. This is the change of energy. And notice as the line drops, we're getting what? More stable, right? Lower energy. So if we're talking about atoms, 2 atoms coming in close contact, now they're free atoms. If they're free atoms, my friends in chemistry, there's our baseline. There's our 0 line. And as they come in close enough contact and start overlapping like a nice covalent bond, we can see that there's an energy drop. And this energy drop is the change of H of formation for that element, okay, or that compound. Now they're showing a positive value because they're calling this the bond energy, the energy it takes to break a bond. Now remember, the bond energy, because of thermodynamics, and especially the first law of thermodynamics, the energy it takes to break a bond is the same energy it takes that's released when you form a bond. So in this case, going right to left, we're showing a release of energy from this free atoms or elemental states down to the bonded port here. That's the parallel here. That is what is very similar. So there is a negative delta H of F as bonds are made. We know that from their elemental states. So again, what's different about this? Well, one little point that has to be made here is that when an atom finally bonds and reaches maximum stability, it doesn't stay in that state. It can really absorb thermal energy, infrared radiation, and therefore thermal energy is motion energy. And these things can vibrate once they're bonded. Sometimes when they vibrate, they push away from each other and become what? Less stable, and they go from this position and up. If they what? If they absorb energy, like for instance, light that hits the planet that bounces back up, or I should say infrared radiation, can hit this chemical and cause it to absorb some motion, and it becomes more unstable and goes up this way as the elements vibrate away from each other. Now, of course, things tend to go towards stability. It's one of the driving factors. What's going to happen is this can give off that vibrational energy and jump back down. But it can also give off more than it had and also start climbing up this way. If it climbs up this way, that means it's vibrating or getting too close, and the 2 nuclei that are positive here start repelling. So what really happens is that atoms are not static. They're constantly vibrating, which means they're pulling apart and they're going toward each other. So the distance, the bond distance or bond length Okay? You should already know the shorter the bond length, the stronger the bond, but that bond length isn't static. Neither is the bond energy. We're constantly up and down this slope. Yes, it eventually rests here for a while, but by gaining energy, by being pushed together or being pulled apart, they're constantly going back and forth. So that's why bond energies are called averages and not the best way to get delta H's. They're limited by the fact they are not static. They're constantly moving. So the bond energy data we get, we try to use averages to get the pluses and minuses out, but still, because of the molecular motion they constantly have, it's not, by the way, the best way to get delta H's, but we still can. Now, how do we do that? So here we are with our reaction again, and let's look at this from the bond energy perspective. So we still have our free atoms up here. Our free atoms, our free elemental states. Okay, so we have our free elements, unbonded, or we'll just say our elemental states. And here's our baseline. It's the 0. So there's our baseline. Okay, and we know from heat of formation that's how much energy is released to get to this position, and there's more here. But in bond energies, what we're doing is we're using the energy it takes to break the bonds. So in every chemical reaction, it takes energy to first break the bonds. Let's review some things. We've learned in the previous years that in every chemical reaction, there's an exo or an endothermic reaction. Either you're overall gaining energy endothermically or you're overall releasing energy exothermically. And when you do so, it gets lost in the shuffle that there's both of those things happening in every reaction. So in order for propane to react with oxygen, these atoms have to break away from each other. Chemical bonds have to be broken, and then they can rearrange. So we're always breaking bonds. So the reactant side is always breaking bonds. So let's just write that. Okay, we have to break these bonds in order for them to rearrange into a more stable scenario. And here we're forming bonds. All right, so now in order to break bonds, we have to add energy. Now, well, how much energy do we need to break them into free elements? We need this amount of energy. So this energy here, from the position they are all the way up, that's the energy to break the bonds. Maybe saying, well, that's just the opposite direction. Correct. Energy to break bonds, because we're going to break them into their unstable scenario. Okay, and of course, once we have them into their free elements and being unstable at our baseline level, then they're going to reorganize themselves, and then they're going to release energy to get to the stable position. And that is the heat of formation collectively of the CO2 and water that we talked about. But we're going to change this arrow the other way. And the reason I do so is because bond energies are always measured by breaking them, even though the energy released in forming the bond is the same energy it takes to break the bond. So my friend in chemistry here, really the energy it takes to break these bonds, okay, is this amount of energy. So although in bond energy, we know to get to this position, we're going to reform bonds. And of course, that's the heat of formation. But in bond energy, we look at it in terms of, hey, if something is what? More stable, then my friends, it's going to take more energy to break. So stronger bonds being lower in energy, meaning a lot more energy was lost when they formed these bonds. So strong bonds, if you remember, mean that you're more stable because there was a lot more heat lost in forming them. So to break bonds, we need more energy here. So essentially, we're looking at the arrows, okay, going up in terms of bond energies. So we're going the opposite way. It's really the same thing, but a different direction. And there's the key. Different direction, okay, means that the signs are going to be different. So when we did heats of formation, okay, we did heats of formation, we said how much energy was needed to form that. That was a heat of formation. And then how much energy was needed to what? Form this. That was also heat of formation. So we're going the opposite direction. Okay, so because the signs are different, because the direction is different, so will the signs. So if I was to use how we determine heats of formation, or delta H from heats of formation, using the summation of the heats of formation of the products per mole minus the summation of the heats of formation of the reactants per mole, reactants per mole. If we were to use this method for bond energies, we would get a positive value because the what? The direction is different. Case in point, let's make this heat of formation, okay, or this value from here to here, let's make it 20 joules. It's not, but let's just make it 20 kilojoules. So it's negative going down, but going up, it's positive 20 kilojoules, correct? Same thing over here. The energy to break these bonds, let's make that positive 40 kilojoules. Whereas the other heats of formation would be negative 40 kilojoules. Remember, thermodynamics is about directionality. So when we look at this, if you were to plug this in, let's do it the same way using bond energies, so the summation of the bond energies. If we would do products minus the reactants, okay, and I probably should write that in green to color coordinate. So 40 minus 20 kilojoules would give me a positive 20 kilojoules for the delta H. Don't forget, your delta H is right here, the difference, the state function. Okay, it's a difference, and it's got to be negative. We want it to be negative, I should say, because we want to show that energy change dropped. The change of this energy dropped in this reaction. That's why it's exothermic. So we cannot use the products minus the reactants. So therefore, party people, when we do this, okay, we have to make sure that we do reactants minus. So delta H, we're using bond energies, the summation of the bonds broken, okay, so it's the bond energies of the reactants, that's the bonds broken, minus the summation of the bond energies, I should say, per mole of the products, which really means the energy released when we form them. I know I have this arrow going up, but generally speaking, you break the bonds, follow the green arrow, and then of course, down the green arrow, we release energy. Okay, so this is essentially the same thing as heat of formation, but that arrow, when we use bond energies from our tablature, as we're going to show you in another sequence of this, is always going to be positive. We're always showing how much it takes to break, so how much energy we need to get to the zero line. So I hope you can see that we have to use reactants minus products for bond energies because we're going the opposite direction. All right, so that's a very, very important distinction, and I'll tell you what, students tend to always forget this for bond energies. They get so locked with products minus reactants and not truly understanding what this is doing here that they forget this. Okay? So an example of this would be something like this. So I want to know the heat of formation. I'm sorry. I want the overall delta H of the reaction, sometimes called heat of reaction, of this. So what I do is I take my reactants and I look at H2O2. Now I drew it this way, but of course it would be drawn something H2O2, and two of them would go to water. It's a decomposition reaction. This is O2. But I kept it this way so you can see the bonds. And you can do Lewis dot diagrams to see this, but you have to be able to. So in any case, how do I do this? What was the energy it takes to break the bonds? Well, there are some bond energies here. So you have to identify the bonds. Well, there's a couple different bonds here. We have a HO bond, sometimes called a HO bond. Yep. And then we have an O bond, or O to O bond, U bond. How many do we have? Well, because there's a 2 in front, we have, well, in one of these we have 2 hobonds. But because there's a 2 in front, we have 4 hobonds, right? For every one of these, there's 2 H to O bonds. Because I put a 2 in front, now I've got 4. So 4 times the bond energy of the H2O plus, well, wait a minute here, there's one O to O, but a 2 in front makes that have a what? Makes that have a 2 O to single bonded O. So basically what I'm doing is looking at the individual bonds and figuring out through stoichiometry how many, because again, we're dealing with delta H, it's not Q. I'm looking at per mole of something. So this is the total energy, the sum of all the bonds in this reaction, of course, per mole. And this is all the energy it takes to break the bonds minus the energy that was released to form them. So what kind of bonds do I have here? Well, I have 2. Each water has 2 O to H bonds, but there's a 2 in front, so guess what? There's a 4 H to O bond. And then I'm going to add 1 O to O double bond. That's different from an O to O bond because we have that pi bond there that adds extra stability. Okay? Now you can probably see that, wait a minute, I have 4 HO bonds that are broken and 4 being formed. Couldn't I cancel that out? You are absolutely correct. You don't even bother with that. So the difference here is essentially going from what? 2 oxygen single bonds to, okay, this 1 O double bond. And if you can tell that this double bond is more stable than a single bond, so we should be an exothermic reaction. But we've got to pull up our bond energies to see this, to plug this in. So we've got 2 times the bond energy of the O to O bonds. Let's go find that. 2 times the O to O bond. And it'll pull up our bond energy term, and here let's go. And our O to O single bond is right here, 146 kilojoules per mole. All right, so 146 kilojoules, and that's the sum total because we canceled out, minus our oxygen to oxygen. We only have 1 here in our balanced formula. So let's go bring that back and go O to O. And O2 is a double bonded. You should know that O2 does have the double bonds. That's 495 kilojoules per mole. So 495. And let's do the math. So what we get here is negative 203 kilojoules. Okay, clearly this number is less. So obviously we started high and went a little lower, and that difference is negative 203. But wait a minute, that's not delta H yet, okay? Because delta H you have to report per something. So normally we report it for the reactant that decomposed. And notice something, there is what? 2 moles. So we should really divide this by 2 moles of our reactant. And when we do that, that 203 divided by 2 gives us a 101.5, or we'll round up to 102, and that's 102 kilojoules per mole of reactant. Normally they define it by the reactant, and you're going to get a negative sign. But the bottom line, it was reactant bond energy minus the product because of what we learned in terms of these arrows going basically up to the what? Free zero sign, changing the signs. So I want you to continue on with the bond energy worksheet and finish that out. Okay, thank you.